So in this video, we're going to go through the rest of homework 12. But the way that this video is going to work is I'll do like the first part with you. I'll show you like how to do A and B. And then you're supposed to pause the video so that way you can set a timer so that you can go through and actually work on those ones in that section. So there's the plan. We've already finished problems 1, 2, 3, and 4. So we'll be working on 5 through 7. And again, just because it's not in this screen capture. Archie, what are we barking at? Might have to go investigate. Okay, number 5, identify the type of intermolecular force involved. Sketch the interaction between two molecules of the same type. Then arrange the compounds from expected lowest to highest melting point. Okay, in order. So helium is a noble gas. Helium is just this helium. Sounds pretty simple. So I'm going to draw, I'm literally just going to draw 2 heliums here. 2 heliums by themselves. They're both like non-polar. They're not even bonded to anything. 2 heliums, the only thing they might be able to do is they each have 2 electrons. So maybe if like their electrons are moving around, maybe they could polarize and slosh around a little bit. So the only possibility for any intermolecular force would be London dispersion forces only. All right, the next one, HCl, this one's gonna be a little bit different. We have the hydrogen, and we don't really even need to draw like the structures between, like if you know how to do the Lewis structure, that's fine. If you just want to draw this, that's okay too. We're just doing H and Cl. And looking at just one of them, chlorine is pretty electronegative. This is from the notes. Chlorine has a 3.0 electronegativity value and hydrogen has 2.1. Anytime that it's between 0.5 and 2.0, when you subtract them, that means it's polar. So 3.0 minus 2.1 is 0.9. So that is polar. So the chlorine is hogging the electrons towards him. He's partially negative. The hydrogen is partially positive. They're both polar. 2 polar molecules are going to have an IMF there. And this type of IMF would specifically be dipole, or just dipole. And some people are like, wait, but there's a hydrogen, so shouldn't it be hydrogen? Because hydrogen is a glorified type of dipole. Well, kind of, except for the fact that when we do that, we have to look for a hydrogen sandwich between NOF, the hydrogen, and then NOF. So in this case, the hydrogen is there, but it's chlorine and chlorine that are sandwiching it, which is not nitrogen, oxygen, or fluorine. So this would just be dipole. It doesn't meet the criteria for hydrogen, even though there is a hydrogen there. So pause the video and then let's do 4 minutes to complete C and D. All right, hopefully you paused the video and actually worked on these. Now, this is my answer key, and this is something I really wanted. I was actually happy that I had it because on part A, I said this was London only, and that's correct. And on part B, I said, oh, this is going to be dipole-dipole. But in addition to dipole-dipole, dipole-dipole is like the strongest one that it has. But everything could have London in it as well. So I want to, when it says to list like all the types of intermolecular forces, I would have London and dipole. Although if you're asking me what the strongest force is, the strongest one is dipole. For part C, I drew some oxygen molecules. They're both non-polar. Nothing's happening here. So our one and only intermolecular force would be London. On HF, I could just write the word London because everything has London, but then check and see if there's anything else. HF, I have two of them. I've got one here and one here. Fluorine, fluorine, most electronegative element. So he's got the partial negative on his side. Hydrogen, partial positive. And here's my little H sandwich. On the one side, it's bonded to an F. On the other side, it has an interaction with an F. That is hydrogen, which also meets the criteria for dipole-dipole. Like it's a polar molecule, so dipole, but the H sandwich between FON makes it hydrogen. So on this next part, we just got to be careful what the directions say. So on this one, it says identify the strongest intermolecular force involved. So on this one, you only need to list the strongest. The order goes London dispersion is the weakest, and everything has London dispersion. Dipole-dipole is the next strongest, and that's occurring when you have polar molecules. And hydrogen is occurring when not only you have a polar molecule, but you have the H sandwich occurring between the N, O, F kind of on the sides. So I would recommend doing these, drawing them out. And I'll do the first couple with you because otherwise it might be hard to see what's going on. So NH3 nitrogen likes to make 3 bonds and has 1 lone pair. Hydrogen likes to make 1 bond, and if I drew another one up here, I've got 2 molecules, and I'm looking at the intermolecular forces. Nitrogen, nitrogen's one of the 3, NOF. Does this make an NOF sandwich? H, N, N, yes it does. So this one does have London because everything has London. It does have dipole because it's polar molecules. And it specifically has hydrogen bonds / hydrogen forces because of that H sandwich. I could circle all 3 to show what it has, but we only need to list the strongest one involved. Okay, so there's kind of how you're going to do that one. I would recommend that you go through and draw the molecules that you know how to. Let me give you a couple hints on the drawing here. Well, actually, just do your best, and then after we're done with the video, pause it, and I'll help you then with the shapes. Just skip the ones that you're having a hard time with. Let's see, A through Z, we got the whole alphabet. So you spend 30 seconds on each. Let's do 10 or 15 minutes. Start with 10. If you need longer, you can take 15 minutes on this and really go through and get this drilled in. Because remember that this chapter in particular takes up almost twice as much of the AP exam as any other chapter. It's like 20%. So you really got to know these. So pause the video and then we'll work through them. All right, welcome back. So on B, it's just a krypton, just a single atom. When you see things like that, just a single atom, it's kind of a dead giveaway that it's going to be London dispersion, because there's no way it can even be polar if it's just a single atom all by itself. And if it's not even dipole, like it can't be hydrogen. So single atoms by themselves, dead giveaway that it's London dispersion. HCl, H bonded to Cl. Chlorine is fairly electronegative. You could confirm that in your homework here, looking at chlorine, as it has a 3.0. 3.0 minus 2.1, 0.9 electronegativity difference. So this molecule for sure is polar. So it does have London because everything has London. It does have dipole because it's a polar molecule. Is this going to make an FON sandwich? No? All right. Then dipole is our strongest. F2, fluorine is electronegative. It pulls at a value of 4. But if it's bonded to another fluorine that's pulling at a value of 4, then it's not skewed. Then it's nonpolar. If it's nonpolar, the only thing it can have is London dispersion forces. SO2. SO2 is polar. If you look up the S and the O values, it will have London dispersion, but its dipole forces are stronger. And there's no possibility for it to have hydrogen because it just has sulfurs and oxygens. There's not even a hydrogen in there. Same thing with CO2. Like, there's no way it can have hydrogen forces because it's carbons and oxygens. Carbon dioxide here. Now this one's going to be different. Let me draw out the difference between silicon dioxide. I think it has one lone pair. I could be wrong. It might have two. But because of the bent shape here, this one is polar. This one is non-polar because this shape, right, cancels out. These polarity arrows do not cancel out. So where this one's polar and becomes dipole-dipole, the CO2, since it's non-polar, the most it could have going on would be London dispersion forces. C3H8, you don't even have to know how to draw that. Like if you're trying to draw it, that's cool. Don't worry about it too much though, because if it just has carbon and hydrogen in it, carbon-hydrogen bonds are always going to be considered non-polar. So if the molecule has just carbons, just hydrogens, and it's non-polar, then its only possibility is London dispersion forces. CH3Cl, let me get some new scratch paper to do this problem on. Carbon likes to make 4 bonds. There's 3 hydrogens and a chlorine. The carbon-hydrogen bonds are non-polar. but the carbon chlorine bond would be polar. The electrons are getting pulled more towards chlorine. So it is going to have London dispersion forces. They always do. It is a polar molecule, so it will have dipole. The question is, does it have hydrogen bonding? Maybe, because it's got hydrogens. But remember that for hydrogen bonding to occur, it has to be a NOFH sandwich. So like somehow we've got to have a bond this way, like to one of these things, and interactions this way. Every single one of these hydrogens is going to a carbon. None of them have N, O, or F. So even though there are hydrogens present, it does not have the hydrogen sandwich we're looking for. HF will though. H bonded to F. Oop, yep, there it is. Because with two molecules, we've got the H bonded on one side and the interaction. That one has all three. All right, let's see. I'm not going to give you all of these because I did give you some hints. But let's see. Are there any ones that are quite tricky? This one's a little tricky. I'll come to that one. Cross out this one. This one shouldn't be on the list. This isn't something that we haven't learned yet. So we're going to cross that out. And the rest of these should be within your ability to do. So the reason I've got ZEF4 there is because I just wanted to remind you of the shape of this. Four fluorines and some lone pairs on that molecule. We will remember how to draw these. And the fluorine is electronegative, but I want to point out that those, since they're 180 degrees apart, and those, since they're 180 degrees apart, all of the polar bonds will cancel, making this a non-polar molecule. If that's a non-polar molecule, then LDF is the only one it can have. So pause this video if you need another second to work on these. I am going to go through and give you the final answers here. And please, please, please email me if you have any questions on this, but I want you to at least have your paper done so that this, when you check it, it'll be worthwhile. But please do email me if you have questions. So this one is London, because all of those are non-polar. This one has all three. Hydrogen is the strongest. London dispersion forces, because it's just a single atom. PCl3 has a lone pair on top like this. It's a polar molecule because it's skewed. So dipole, dipole. Maybe if you drew it wrong, you thought that they canceled out, but they don't. HCN is a polar molecule, but if you try and make an H sandwich, it doesn't work. Carbon monoxide is also polar, single molecule or single atom all by itself. Water is polar, and it does make the H sandwich. 4 P's all pulling on each other in some fashion. The most you're going to get is London, London, SF4. Okay, so I think the way that that one bonds, I really need to brush up on this, but I think that this one looks like this, and it's a polar molecule. If it's a polar molecule, then it's going to be dipole-dipole, and I think that's how it's drawn. I would need to double check, so don't stress out about that problem too much. Same thing with pH3, it's going to look very similar to the PCl. And I2, two iodines pulling on each other equally, non-polar, so London dispersion forces. Usually on the AP test, they don't just ask you to list the forces, they'll ask you questions like this. Which of the following would be expected to have a higher melting point? And you're like, well, what does melting point have to do with intermolecular forces? And you've missed the whole point if that's your question. Because the IMFs are trying to sticky things together. If it's stickying things together really, really good, then it's going to take a lot of heat and a lot of energy to get them to melt apart. So the more IMFs that you have, this is the conclusion, the more like stronger IMFs you've got, the higher you have to crank that heat to get them to melt apart again. So go through and try and decide. I'll do A with you right now, Cl2 or Br2. I'm looking at this going, well, two Cl's bonded together. Chlorine, chlorine, okay, big whoop. Bromine, bromine. Fantastic. They're basically the same here. They're both non-polar, non-polar. So they both only have LDFs. Which LDFs will be stronger? So check back in your notes and look and see what would make an LDF be stronger than a different LDF. LDFs increase with increasing polarizability, aka with more electrons. LDFs increase when they're more straight. That one doesn't really apply to us because it's just two atoms bonded together, but the first one certainly does, because bromine has like 35 electrons. Chlorine only has 17 electrons. So because this one has more electrons, it's going to have a higher polarizability, which means increased London dispersion forces. So that's how you're going to approach these. The last problem as you're getting to it, where it asks about pentane or dimethylpropane, both of them are C5H12, but this shape is the dimethylpropane, kind of a rounded shape there. And this one, more of a kind of a brick shape going straight. So let's see, A, B, C, D, E, F, G. Let's take 10 minutes because you're gonna have to look these up, but 10 minutes for this section before we get answers. So pause the video. And welcome back. Here are my answers for this section. Let me zoom in, crunchy noises. So just like I said in part A, the Br2 is going to have stronger IMFs because the more electrons means more polarizable. More polarizable, stronger LDFs. Part B, this is a bigger molecule, 5 carbons, 12 hydrogens versus 4 carbons and 10 hydrogens. More electrons, same argument, more electrons, more polarizable. NH3 is going to have stronger forces than PH3 because the NOF, the N there, can make that hydrogen sandwich where the P can't do that. The PH3 only has dipole-dipole, but the NH3 has the glorified, glamorous hydrogen bonding. Now this one's kind of a trick question. It's not actually looking at IMFs. These are ionic bonds, but the question could still be asked which one has a higher melting point, BeO or KCl. BeO versus KCl. Ionic bonding, they came from ions. Beryllium is in the 2+ column of the periodic table. Oxygen is in the 2- column. So that's how the beryllium oxide came together. Potassium chloride, +1 column, -1 column. So if we're trying to figure out which one is stronger and would take more heat to melt because it's more strong in its attachment, I'm going to say this one because 2 positives and 2 minuses, that's like a double magnet attracting versus just some single charges. So in my paper, I wrote greater charge on ionic lattice. Part E, ICl, the iodine and the chlorine don't pull on each other the same. It will be polar, so it has dipole forces, whereas the bromines only have London dispersion. So of course, dipole is going to beat out London dispersion. HF and HCl are both polar, but HF can make the hydrogen sandwich, which is stronger. And on the last one with the fact that both are C5H12, the more boxy shape they are, the straighter they are, the more energy this is going to take. So the pentane is going to have more London dispersion forces because of its straight shape. So there we have it for, that was notes, that was all of notes. I think we should, at this point, we're done with notes 12, and we're also done with homework 12. So make sure to get those in. I did complete the entire homework with you, so you should be getting just right in on the top 10 out of 10. But if you have questions on the homework, leave me like your question in the comments. Like, I didn't really understand number 3 part whatever, and then I'll go through and can comment back to try and help you with those. So there we go. That's it for notes 12 and homework 12.